I now call to order the Society's 2,400th meeting in the 148th year since its founding in 1871. Good evening, everyone. My name is Larry Milstein. I am the president of PSW, one of the oldest scientific societies of Washington, D.C., dedicated to providing a forum to further scientific understanding and inquiry. Welcome to our members and guests to tonight's lecture by Dawn Tilbury in the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C., including our members and friends around the world who are watching the live stream of tonight's meeting on PSW Science's YouTube channel. Today we are celebrating the Society's 2,400th meeting, an average of 16.1 meetings per year, over 148.75 years since its first meeting on March 13th, 1871. At the end of the meeting, please help yourselves to a piece of the celebratory cake. That is, at the end of the meeting during the social hour. You can't do it now because it hasn't been brought down yet. We will begin with a few announcements, a reading of the minutes of the 2,399th meeting, and a lecture by Stephen Squires on the proposed CSAR mission. We will then turn to this evening's lecture, followed by a question and answer period. Thereafter, I will present a small thank you gift to our speaker, make a few closing announcements, and adjourn the meeting to the social hour and cake, hopefully. So please join me in thanking the sponsors of the 2018-2019 lecture series, the Policy Studies Organization, and there may be a representative here from that organization, and the American Public University, and a generous donor who has asked to be made anonymous. Thank you very much. And please join me in thanking the sponsor of tonight's lecture, PSW member Robert Terry, also known as Bob, who is easily recognizable because of his very bright, beautiful red jacket. Thank you, Bob. I'm pleased to announce that the following new members have been elected to the Society. Brian Hart, serving in the U.S. Navy, interested in X-ray astronomy and public service education. Lisa Tibbetts, a biomedical data analyst with Perthera, with broad interests in science, especially cosmology. And Noah Block, serving in the U.S. Air Force, interested in basic physics, astronomy, and space exploration. And finally, tonight's speaker, Dawn Tilbury, whose background and interests will, in part, be clear to you from tonight's proceedings. Please join me in welcoming them to the Society. I have for each of the newly elected members and any previously elected members who have not got one, a signed copy of Volume 1 of the PSW Bulletin, which will explain in detail how PSW came to be called originally the Philosophical Society of Washington, which, as explained there, does not mean Kant, Hegel, Plato, and Socrates. It refers to natural science, which was the term at the time for science. Recording Secretary James Heelan will now read the minutes of the 2,399th meeting and the lecture by Steve Squires on the proposed CSAR mission delivered here at the Cosmos Club on November 2nd, 2018. Podium is yours, James.
Thanks, Larry. Hi, good evening. As Larry mentioned, on November 2nd, 2018, President Larry Milstein called the 2,399th meeting of the Society to order at 8:04 p.m. here at the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C. He announced the order of business, that the evening's lecture would be live streamed on the internet, and welcomed new members to the Society. The minutes of the previous meeting were then read and approved. President Milstein then introduced the speaker for the evening, Stephen Squires, the James A. Weeks Professor of Physical Sciences at Cornell University. His lecture was titled, The Proposed CSAR Mission to Return a Comet Sample to Earth. Recorded history reflects long-standing human fascination with comets. And although comets have solid nucleus, they are so rich with volatile material that scientists have not been able to identify the remains of any comet that has collided with Earth. Squires said comets are planetesimals, preserving what he called the leftovers of the early universe. He said comets were the major source of Earth's early organic chemistry, and as such, comets are a source of information for the origins of life. The New Frontiers program competitively selects NASA's planetary missions. There are 2 finalists for the next New Frontiers selection: the proposed Dragonfly mission to Titan and the proposed Comet Astrobiology Exploration Sample Return, or CAESAR mission, for which Squires is the principal investigator. New Frontiers is scheduled to choose the winning proposal in 2019. Returning a sample will be invaluable, Squires said. Laboratory instruments are orders of magnitude more capable than those that scientists can miniaturize and launch into space. Samples can be re-examined far into the future with more advanced technologies. Moreover, going to a comet in space is the only way for scientists to obtain a sample of a comet's volatile materials. CAESAR therefore proposes to take a sample from the comet Churyumov-Gerasimenko, the comet nucleus previously visited by the European Space Agency's Rosetta spacecraft. Because scientists already know what the comet nucleus looks like, Squires says his team has been able to identify a prime sample site and design instruments around it. The CAESAR spacecraft will have a solar array 43 meters from tip to tip, a high-gain antenna, and a single suite of cameras. The mission will be powered by a solar electronic propulsion, which accelerates xenon to produce a gentle thrust that may be powered for years at a time. CAESAR would launch in 2024, arrive at Churyumov-Gerasimenko in 2030, conduct operations until 2032, and arrive back on Earth in 2038. CAESAR will use touch and go, or TAG, sampling, involve a descent to the comet's surface, brief contact to obtain a sample, and a quick departure from the nucleus. Squires described CAESAR's sampling arm as a pogo stick, in which there is a compressible constant force spring to hold in place the sampler mechanism, which Squires then described in detail. Squires also described CAESAR's containment system, designed to ensure the comet volatiles survive the return trip to Earth. The CAESAR team believes it will be able to return a 200-plus gram sample from the comet. The team will examine only 25% of that sample, with 75% of it preserved for future investigators. In the question and answer period, a PSW member asked how many chances CAESAR will have to obtain a sample. Squires said CAESAR will have enough consumables for 3 full sampling attempts, with each full attempt preceded by 2 rehearsal attempts. Another member asked what unique research benefits Squires expects from a sample rather than from remote observation. Squires said, to obtain highly precise measurements of stable isotope ratios. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. At 9:46 p.m., President Milstein adjourned the 2,399th meeting of the Society to the social hour. Temperature, 19.5 C. Weather, rain showers. Attendance in the Powell Auditorium, 96, and viewing through the live stream on the PSW Science YouTube channel, 40. Respectfully submitted, James Heelan.
Corrections, additions, comments on the minutes? Hear none, I will entertain a motion to accept the minutes as read. It's a second. All members in favor? All members opposed? Hearing no opposition, the minutes are accepted unanimously as read and will be posted to the website in due course. It's my pleasure to introduce tonight's speaker, finally, Dawn Tilbury. Dawn is Assistant Director at the National Science Foundation, where she heads the Directorate for Engineering. She is also Professor of Mechanical Engineering and Electrical Engineering and Computer Sciences at the University of Michigan, Ann Arbor. Dawn's research has been broadly in the area of control systems, including applications to robotics and manufacturing systems. She is an author on more than 150 articles in refereed journals and conference proceedings, and she is co-author of the textbook, Feedbook Control of Computing Systems. Among other honors, Dawn is an elected fellow of the IEEE, an ASME fellow, and a life member of SWE. She is a co-awardee of the EDUCOM Medal, as well as awardee of the AACC's Ekman Award, the SWE Distinguished Engineering Educator Award, and the Ravens Leadership Award of the ASME Dynamic Systems and Control Division. Dawn earned her BS in Electrical Engineering at the University of Minnesota and her MS and PhD degrees in Electrical Engineering and Computer Sciences at UC Berkeley. Please hold questions for the question and answer period at the end of the lecture, and join me in welcoming Dawn to the podium.
Thank you. Well, thank you very much. It's great to be here tonight to tell you a little bit about the National Science Foundation and our 10 big ideas that we've put forward as areas we think are really ripe for future advancement. So many of you, I'm sure, are familiar with the National Science Foundation. Let's see if I get the right clicker. So we were founded right after World War II. After the war and all the technology that the U.S. had invested in and used to really come out successful after the Second World War, it was recognized the importance of basic scientific research and how that was important to national security, both for military and commercial reasons. And also that continued government support was really required to keep that superiority in technology and science. So the Vannevar Bush was one of the people working in the government at the time, and he wrote this report and gave it to President Roosevelt, called Science, the Endless Frontier. And he said that basic fundamental scientific research is really the pacemaker of technological progress. And new products and processes don't just appear fully grown. You need to build on the new principles and new conceptions which are developed in turn by painstaking research in the purest realms of science. So unfortunately, President Roosevelt didn't live to found the National Science Foundation, but President Truman signed the act that formed the National Science Foundation 70 years ago with the mission that you see here on the screen: to promote the progress of science, advance the national health, prosperity, and welfare, and to secure the national defense. You see that in front of our brand new building. We moved in just over a year ago, and we're located just at the Eisenhower Avenue Metro on the Yellow Line, which is closed right now, but you can get there on the Blue Line if you want to come. Anyways, so NSF is today the only federal agency that funds fundamental science, high-risk, long-term, curiosity-driven research in all fields of science and engineering. And that's shown on this picture here. You can see all the different fields of science that we fund at the National Science Foundation, from astronomy, unlocking the secrets of the universe, to zoology, understanding how animals behave. We also run the U.S. Antarctic program with several bases on the continent, and I had a fabulous opportunity to visit there last year, but that's another story. So here you see NSF by the numbers. Our fiscal year 18 budget, which we just completed at the end of September, was $7.8 billion. Now this shows the numbers for fiscal year 17 because we haven't parsed everything down to this level of detail for fiscal year 18 yet, but I think this will get updated shortly. They're not too much different. Fiscal year 18 was about a 4% increase over fiscal year 17. And so many of these numbers about numbers of proposals, numbers of awards, you could imagine are increased by a few percent. A couple numbers I'd like to point you to on this slide with lots of numbers. On the far left side, you see 93%. So that's how much of the money that we take in from the taxpayers that we send out the door to universities and other organizations that are doing basic scientific research or educational activities in science and engineering. We're not doing any research ourselves in that beautiful building at Eisenhower Avenue. We're really helping to decide where to send those funds. The other number that I'd like to point you to is almost 350,000 people are supported in part by NSF grants. Those are faculty who are directing those research projects, graduate students who are working on them, undergraduate students working on their undergraduate degrees, doing summer programs in research, etc. And finally, if you look at the number of proposals that are submitted and the number of proposals that are funded, you see it's on the order of 20%. So there's a lot more proposals that we receive that are meritorious and would deserve funding if we had enough money. And by some calculations, if we wanted to fund all of the proposals that we received that the reviewers ranked as meritorious and deserving of funding, we need at least another $1 billion in our budget. So we're not there yet, but we think that there's opportunities to continue to grow the budget. We don't have a budget yet for fiscal year 19. If you saw the news today, we do have a continuing resolution for 2 more weeks. And the House and Senate marks have been pretty positive with another 5% or so over fiscal year 18. So we're waiting and seeing and hopeful that we will continue to grow our budget. But in that context of what NSF is funding across all areas of science and engineering, I wanted to talk to you tonight about the big ideas. So these are the 10 big ideas, as I mentioned, for future investments that we believe at the National Science Foundation are really ripe for rapid advancements in science and engineering that can have significant societal impacts. In my opinion, these ideas can also help communicate our research activities to the general public. Instead of telling my neighbor, oh yeah, the National Science Foundation funds research in engineering and biology, I can say, we're looking at unlocking the rules of life or harnessing the data revolution, things that might make more sense to the general public in terms of what science is doing. All of these big ideas really require collaboration across multiple disciplines. These grand challenges are not going to be solved by people in one discipline working alone. And so progress in big ideas is going to require this breaking down of barriers between disciplines. So as I go through these different ideas, I'm going to spend a little bit more time on some and less on others, but I'm going to start with the ones on the bottom, the process ideas, because I think they're really fundamental to all of the big ideas. If we don't make progress in the process ideas, we're not going to make progress in any of them. And so really when I talk about multidisciplinary, I'm going to start with growing convergence research, which is the picture that you saw in the advertisement for this talk. When we practice science in silos, because of the way that we fund science across those 7 directorates that you saw in the earlier slide, it really limits the potential for discovery. If we want to expand into new frontiers, we need to integrate knowledge and tools from multiple disciplines, representing different ways of thinking. And so convergence is really about addressing big challenges with an intentional approach to address a deep scientific problem or a pressing societal need. We want to enable sustained interactions between researchers from different disciplines in order to produce new frameworks, paradigms, insights, or even new disciplines that may emerge from this integrated research. The idea here is to fund high-risk research that might not be able to find support in the current aspects of NSF because it doesn't fall into our traditional funding or disciplinary divisions. Now, when you stop to think about it, it's not too surprising that originally discipline referred to training of scholars to proper conduct and action through instruction, resulting in a set of rules, right? Discipline, that's what it means. Therefore, when you bring an interdisciplinary group together to solve these problems, you're going to need to break some rules. Things aren't going to be done the same way they've been done before. Now, for some people who like to break rules, this can be really exciting. On the other hand, some people can be fearful of that because it's not the way they've done it, or they might feel that they're not going to get evaluated correctly for their work or might not get rewarded for it. So NSF identifies convergence as having two primary characteristics. The first is a deep integration among disciplines, like I mentioned. When experts from different disciplines come together to pursue common research challenges, their knowledge and theories and methods will become increasingly intermingled and integrated. We believe that new frameworks and paradigms and even new disciplines can form from these sustained interactions from multiple communities. The second aspect, though, is that convergent research is driven by a very specific and compelling challenge or opportunity. You don't just take a biologist and a mathematician and a computer scientist and throw them in a room together and see what they come up with. It's likely they'll come up with something really interesting, but it won't be addressing a specific problem. We'd like to see teams that are addressing current challenges, clean water, sustainable energy, personalized medicine, that require this type of convergent research. Students, I find, are really inspired to work on these big challenges, these grand challenges, but they don't always have the tools to work across disciplines or talk to people working in other areas. So therefore, we also have a challenge to educate students to work in these type of convergent research problems. Research has shown that a common language is really key to build effective communication among team members. As I'm sure any of you can understand, if you've tried to visit a foreign country and you don't speak the common language, it's hard to communicate. And it takes time to learn enough about the other disciplines to be able to collaborate in a meaningful way. Unfortunately, sufficient time doesn't always get allocated at the beginning to facilitate this understanding. I'll tell you a story. A few years ago, I was talking with a colleague at the University of Michigan. She was in the psychology department and was interested in how children control their emotions. Well, I'm in engineering and I have a background in control theory. I thought, oh, control, emotional control, we could try to write a proposal together. So we sat down and we were writing a proposal to the National Science Foundation about emotional control of toddlers. And we're sitting in a conference room writing this proposal, and I'm at the whiteboard and I draw this graph of this variable X that's changing over time. And she was shocked. She told me, variables don't change over time. And I said, of course they change. That's why we call them variable. And she said, no. In this study that we're doing, the variable is whether these toddlers are in the US or in China. Are they boys or girls? And that is not going to change over our 2-month course of study. And I said, well, we're going to strap accelerometers to these kids and see how much they move. And we're going to measure their movement, and that's a variable, and it's going to change over time. If you've ever watched a toddler, their movement changes over time frequently. And she said, well, that's something we're measuring in this experiment. That's a metric, not a variable. So even though we're both speaking English and we're both talking about control, we realized that we were speaking different languages. And if we wanted to come together to do this kind of convergent research, we really needed to understand at a deeper level what each other was talking about. Some very interesting outcomes of that work, but that's for another talk. So anyways, these complex questions that we want to address require new approaches, and convergence requires those interdisciplinary teams to really come together intentionally in novel ways to strategize a research plan that confronts these challenges that are independent of disciplinary boundaries. So NSF sees this convergent research as a really powerful method to solve many important challenges: food, energy, water, pandemics and infections, disaster preparedness and recovery. But we need to give teams the time to come together to learn to speak the languages, each other's languages. You don't need to be fluent in psychology or control theory, but you need to know enough words to be able to communicate. So with a call last year, for convergent research, NSF received more than 100 proposals for people who had ideas to address challenging problems at the intersection of some of these disciplines. And they sent us their ideas on how they would do this and how they would bring these convergent teams together. So there were many challenges, like I mentioned, the environment, human health, energy, food production, and the economy. I'm only giving you 2 examples here, but there are many more that we've funded and many more that are in the pipeline. So first of all, coral reefs. You've heard the stories in the news about how the coral reefs are dying, and it takes a long time for corals to grow. So this team, which is engineers, material scientists, and biologists, have come together to try to engineer foundations for young corals to grow and grow more quickly and more efficiently to reproduce coral reefs when they're in danger. The second project is about our understanding of brain activity through integrating bioengineering, systems neuroscience, and data science. They're planning to develop new sensors to image the activity of individual neurons within a large network, and then apply this network to really study how neural systems function. Many other examples exist, including using NSF-funded supercomputers to find a cure for HIV, or looking at physicians and theoretical physicists and computational biologists coming together to attack pancreatic cancer. So NSF has our own challenges in this area because when we put together a review panel, all of those people are coming from individual disciplines. So we're working to bring not just the research communities together in Convergence, but our reviewer communities together in Convergence, and giving the program officers the ability to fund these kind of high-risk convergent research projects. Of course, we fully intend to continue funding disciplinary research because we need to continue making advances within the individual disciplines to enable these new convergent research proposals. So now let me briefly talk about one of the other process ideas, which is called mid-scale research infrastructure. So this picture indicates the gap, as you can see. The National Science Foundation does not currently have a good way to fund research infrastructure in the mid-scale budget range. If you have an idea for some new research infrastructure that costs less than about $7 million, send it to the MRI program. If you have an idea for a brand new telescope or a ship that's going to cost more than $100 million, we can fund that through the MREFC program. But anything between about $7 and $70 million is in that gap. And we can fund it, but there's no established mechanism. And so what we have been doing in collaboration with the National Science Board, who sent a report to Congress on the importance of this mid-scale gap, a plan to come up with a method to fund these kinds of projects. Now, given our budget limitations, I don't expect that we're going to have hundreds of these kinds of projects coming out. But when we sent out a request for information to the community, we got more than 200 responses from people who had good ideas for new types of research infrastructure that could be either construction projects, purchases, or upgrades to existing infrastructure. So our plan is to close that gap in 2 pieces. The first solicitation is out, asking for small mid-scale projects, and the larger solicitation for large mid-scale projects should come out shortly. Now, we expect to receive many more proposals for these kinds of awards than we'll be able to fund, but at least it's getting started. So this next big idea is called NSF 2026, or the idea machine. Now, I mentioned we have 10 big ideas, and we think they're all great, but we realize there's probably a lot of other great big ideas out there in the world. And so we have invited the general public to submit big ideas to us. This website opened up in August of last year. Now it closed at the end of October, so you missed your chance. Did anyone send in a big idea to the idea machine? It was open to anyone in the general public, 14 years of age or older, so we were hoping some high school students would submit. And we did receive more than 700 submissions. So we're looking through those within NSF and evaluating on the criteria of the relevance to NSF. It has to be basic scientific research in an area that NSF funds, and the relevance to society. So what we are planning to do is, after we sort through and winnow that list of more than 700 down to a few dozen, we're going to invite those people to make videos about their ideas, and then invite the general public to comment on those videos. And there'll be another review process, and at the end of the day, there'll be cash prizes awarded to the best ideas, up to $26,000. So why 2026? Well, it's our nation's sesquicentennial, which will be 250 years. So we thought it would be fitting to have a nationally inspired goal to coincide with 250 years of our new experiment over here in America. So now I'd like to talk a little bit about includes. This is the last of the process ideas, and in my opinion, it's one of the most important ideas. This is really a comprehensive initiative to enhance U.S. leadership in science and engineering, discovery and innovation by really developing science, engineering, technology, and mathematics, or STEM talent, from all sectors and groups in our society. If you've read the statistics, there are minorities and women are severely underrepresented in STEM fields, as well as rural communities, inner city communities, and socioeconomically disadvantaged communities don't have the same opportunities to come into science and engineering as their wealthier counterparts. So we want to increase participation in science and engineering from many of the brightest young minds. We don't know where the next groundbreaking discovery or the next big idea is going to come from. And so we want to make sure that we reach the full potential of all students and learners at all levels of society, investing in the people in their educational and career avenues, especially those who have been traditionally underrepresented. We believe that these investments will make for a more creative, more prepared workforce in the future. And it amplifies NSF's, which has a long history of investing in broadening participation. So this is some data from engineering, which is my field. I think it echoes many other fields. Nationwide, you may realize that women receive more than half of all undergraduate degrees at the university level. And over my career, women's enrollment in professional schools has grown significantly. There are now more women than men in the first-year medical schools. Law schools are about half women, and business schools are almost 40% women. However, as this red line shows you, the percentage of women in engineering has been stuck at about 20%. You can't see that it's been stuck at 20% for more than a decade, but that's really where it is. Even though the overall enrollment in engineering has been growing significantly. It's not shown on this chart, but kindergarten classrooms in the US had only a minority of white students last fall. But on the other hand, the percentages of underrepresented minorities in engineering has been moving in the wrong direction, even as the enrollments are increasing. So it was mentioned earlier, I was an undergraduate at the University of Minnesota in studying electrical engineering. And at the time, there were no ladies' rooms in the electrical engineering building. Now, at least the electrical engineering building was connected to mechanical engineering, so we didn't have to walk outside in a Minnesota winter to use the facilities, but you might think that would be one reason why there maybe weren't so many women. At one point, a faculty member told me I should switch out of engineering because it's not a very good field for women. My father was an engineer, and he told me the professor was wrong. Who do you believe? And then when I was getting close to graduation, I got sent a letter by the department congratulating me on my outstanding academic performance and encouraging me to consider graduate school at the University of Minnesota. Now, I'd been in the department for 4 years by then, and they addressed this letter to Mr. Tilbury. And so I took the letter to the professor, and he looked at it, and he's like, oh, I didn't write the letter. The secretary writes the letter, I just sign it. So I took the letter to the secretary, and she said, oh, that's just the default. And, you know, these are some of the kinds of things that those of you who've been around for a while may have come across. So I did go to this event where they were recruiting graduate students because there was free pizza and I was still an undergraduate. And so I did meet up with the professor there, and he came up to me at the event and told me he had told the story to his wife, who told him if that was the way the system works, he should try to change the system. So I was glad to hear that they're working on changing the system, and I did go to graduate school, but not at Minnesota. And they finally built a new electrical engineering building that, of course, has ladies' rooms. This report that came out, many of you might have seen it. It was released right around Memorial Day of this year, and it was funded in part by NSF on sexual harassment of women in academia in science, engineering, and medicine. And so I want to summarize a few key points from the report, but I think this iceberg picture on the right-hand side is a great metaphor for how this works. And you can download this iceberg picture from the National Academy's website if you're interested. So sexual harassment is a form of discrimination that has three types of harassing behaviors. There's gender harassment, which is defined as verbal and nonverbal behaviors that convey hostility, objectification, exclusion, or second-class status about members of one gender. The second type is unwanted sexual attention, and the third type is sexual coercion. And it's those two second and third types that are above the waterline on the iceberg. They're the ones that people see in the news reports, Harvey Weinstein, etc. The first type, gender harassment, is below the waterline. It's actually the most common form of sexual harassment, but not everybody realizes it as sexual harassment. And these distinctions are important because not everyone realizes that the most widespread part of sexual harassment is the least recognized. The report summarizes it as saying, it's the put-downs, not the come-ons, that are driving women out of science, engineering, and medicine. So sexual harassing behavior can be either direct, meaning targeted at an individual, or ambient, meaning there's a general level of sexual harassment in an environment, and it's harmful in both cases. The two characteristics of environments that are more associated with higher rates of sexual harassment are A, environments with male-dominated leadership and gender ratios in leadership, and B, an organizational climate that communicates a tolerance of sexual harassment. An organizational climate that is the greatest predictor of occurrence of sexual harassment is ameliorating the environment, and creating an inclusive environment can prevent people from sexually harassing others. So environments that have organizational systems and structures that value and support diversity, inclusion, and respect are environments where sexual harassment is less likely to occur. In other words, sexual harassment often takes place against a backdrop of incivility or an environment of generalized disrespect. So we want to create environments where everyone is respected and supported, no matter their gender. This report did not address minorities in science, engineering, and medicine, but I believe many of the findings would also apply to other minority groups. So the report has many recommendations for federal agencies and other organizations. And the NSF has many efforts underway to help these organizations and institutions improve their climate. You may have heard about the NSF Advanced program, which works on improving the climate for women faculty in science and engineering. We had one of the first advanced grants at the University of Michigan, and through that experience, I learned that the policies and practices that the university put in place to make life better for women faculty, such as transparency, fairness, flexibility, really made life better for all faculty, including the men. So it's not something specific just for women, but if you make things better for women, you tend to make things better for many. So NSF INCLUDES is where I started before I got into the numbers and the sexual harassment, is a comprehensive effort to focus on broadening participation, as you can see by the tagline here. Now NSF has been investing in broadening participation for decades, and there are many successful programs, bright spots, small-scale successes. Companies have been investing in this broadening participation. Funding agencies across the government and private funding organizations are also really important. Think that this broadening participation is important. But how can we really make the needle move? As I mentioned, that percentage of women in engineering has been stuck at 20% for more than a decade. So the research shows that in order to make significant change, you need to bring people together in partnerships. So NSF Includes is using a collective impact approach with multiple teams of partners working together to address the same problem from different aspects and with different tools. And a network is being built starting from 70 small-scale launch pilots, I think this number's here, including more than 800 partner organizations. So these complex problems, such as overcoming the barriers that many groups face in accessing STEM opportunities, are best addressed through these structured collaborative partnerships focused on finding solutions through common goals and shared metrics. So recently, Boeing announced an $11 million gift to NSF to accelerate training in critical skill areas and increase diversity in science, technology, engineering, and math fields. Boeing became the first business partner of the NSF Includes National Network, with an aim to enhance U.S. innovation leadership through broadening participation. Part of the Boeing gift to NSF will focus on increasing the number of women in STEM fields, particularly women returning to the workforce and veterans. Earlier this week, at this rollout of the STEM Education Strategic Plan, NASA announced a collaboration in support of the NSF Includes networks. And over the coming months, NASA will work with the NSF Includes community to better understand how NASA's unique assets can support the participants in the NSF Includes National Network and broaden participation in all STEM careers. NSF will continue to build on the NSF Includes National Network, hopefully incorporating more government agencies, more private companies, and other people, universities, and private foundations that are interested to contribute to this NSF Includes National Network. So that's the end of the 4 process ideas. I've focused on 2 of them because I think they're the most fundamental and will help with all of the others. So now let's work on the research big ideas. So we have 6 research big ideas, and I'll talk through all of them at least briefly. We think all these ideas are big, but we're going to start with the biggest one. Windows on the Universe is really trying to explore the biggest mysteries of all, the origins and the composition of the cosmos. Humans have been looking into the heavens since the beginning of time, and Galileo introduced technology, the telescope, that offered a deeper and more expansive view of what was up there. Every year, every decade, telescopes get better. We can see more, we can see further, we can see more detail. We've been making observations across the known electromagnetic spectrum, from radio waves to gamma waves, and many great discoveries have been made. We've been capturing particles and other matter that arrives at the Earth, meteorites and neutrinos. Last year, NSF and our collaborating institutions announced that LIGO had, for the first time, detected gravitational waves on Earth, the result of a collision of 2 large black holes 1.3 billion light years away. Although Einstein predicted the existence of gravity waves more than 100 years ago, he thought the effect was of no practical interest because it was too small to be detectable. However, NSF invested more than $1 billion over 40 years to build these detectors, with the promise that someday we might be able to sense it. Over that time, they needed to increase the sensitivity of the detectors by 7 orders of magnitude, which is an incredible engineering accomplishment and opened a new window into previously undetected phenomenon like merging black holes. This past summer, researchers published data that had been gathered at NSF's IceCube, the neutrino observatory embedded in the ice sheet at the South Pole, that points to the answer to another century-old question. What's the origin of high-energy cosmic rays? The detection, a few neutrinos going through the ice sheet at the South Pole, was confirmed by other instruments, including an orbiting telescope operated by NASA, demonstrating the value of this emerging field of multi-messenger astronomy, where we see things that happen far away and they send signals to the Earth from multiple sources, the single source, but multiple messengers that reveal new things about our universe. So answering these long-held questions with bold, big instruments will be the first time on this planet we have the wherewithal to take electromagnetic waves, particles, and gravitational waves observatories to focus them on different parts of the heavens and learn new things that were previously unimagined. So let's come out of outer space and down to Earth and talk about the Arctic. The Arctic, as you may have heard, is warming 2 times the rate of the rest of the planet. And the consequent melting of sea ice and permafrost raise both environmental and human habitation concerns. The Arctic change will fundamentally alter the climate, the weather, and the ecosystems in the rest of the world in ways we don't yet fully understand, but we will have profound impacts on the world's economy and security. You may have heard in the summer of 2017, the first ship to traverse the Arctic Northern Sea Route without assistance from icebreakers completed its journey. This transformational moment drives home both the opportunity and the imperative for the United States and one of the nations with an important Arctic presence to ready itself for the new Arctic. Rapid loss of sea ice in the Arctic and other changes will bring new access to the Arctic's natural resources, fossil fuels, minerals, fisheries that were previously unreachable. According to the U.S. Geological Survey, the Arctic region itself holds an estimated 13% of the world's undiscovered oil and 30% of the undiscovered natural gas. You can imagine that this new access to fuels is already attracting international attention from industry and nations that are seeking new resources. We're currently limited in our understanding of the effects of the changes and their challenges and opportunities because of sparse sampling of the land and ocean. Research in the Big Idea of Navigating the New Arctic plans to document key aspects of this changing Arctic, coupled across terrestrial, marine, global, atmospheric, and social systems, and the sea ice retreat and the thawing permafrost, and how they will impact social systems and marine commerce. We're also looking at the design and engineering of sustainable and resilient urban and rural civil infrastructure in a rapidly changing environment. We're planning to build a dense network of sensors across Alaska that will include cheaper technologies such as 3D printed sensors and autonomous sensors in the ocean and atmosphere, allowing researchers to document changes in the Arctic land, sea, and air. We've also funded a project to develop and demonstrate new robotic technologies for persistent autonomous observation of undersea marine environments. These projects, along with many others, and exhibit our commitment to research that can inform evidence-informed policy in the Arctic. Now let's focus from the Arctic more closely on Earth to living systems and ask the question, is nature predictable? The goal of the Big Idea, Understanding the Rules of Life, is to understand the variation and complexity of living systems from the genome and its epigenome or environment to its phenotype, the observable characteristics of an organism. Now that may sound to you like a purely biological problem, but engineers are really helping to create synthetic cells that reduce life to its simplest essence. Engineering biology, or sometimes called synthetic biology, is an emerging discipline that combines both scientific and engineering approaches to the study and manipulation of biology. For example, we try to apply engineering principles to realize standardized biological parts that can be reliably reused off the shelf to perform specific functions. Rather than asking, how does an existing natural biological system work, synthetic biologists ask, what components are necessary to encode a specific behavior within an engineered living system? Insights gained through understanding the basic biology and chemistry in these simple cells can be used to design and engineer new types of useful reactions, such as producing biofuels or cleaning up and processing toxic wastes present in the soil. On Monday, Frances Arnold, who is an NSF-funded chemical engineering researcher, will receive the Nobel Prize in Chemistry for her work in engineering evolution to produce enzymes that catalyze reactions that don't exist in nature. Her work made it possible to make industrial chemicals without toxic metals or organic solvents, and new pharmaceuticals to attack important diseases. Many of the useful variants that she found would not have been found without the random mutagenesis strategy she proposed. In the future, using the work we're doing in understanding the rules of life, we hope scientists will be able to predict with confidence whether crops will grow in extreme temperatures, and doctors will know which cells will become malignant, and renewable resources can be available economically. Now let's go to the smallest of the big ideas, which is quantum leap. I'm sure you've heard about this in the news because it is really on the hot topic of every congressman's at least agenda. Because it is, even though it's the smallest big idea, it has a big potential. And so new advances and growing international investments in quantum-enabled science and engineering have really been the inspiration for the big idea, quantum leap. No, it didn't come from the TV show. So the initiative really aims to extend our understanding of the quantum world to make new breakthroughs in the developing of new technologies. With quantum phenomena like superposition, entanglement, and squeezing, we believe we can have the next wave of precision sensors, more efficient computations, simulations, and even communication. Engineers are designing new devices and networks that can enable us to take the quantum leap and start using quantum physics, so-called spooky action at a distance, to revolutionize computing and communication. Someday you may have heard that quantum computers are going to crack all of our cryptography codes that we've been using to secure our banking systems. But on the other hand, quantum cryptography could turn out to develop ultimately unbreakable cryptography due to the laws of physics that govern the coherence between coupled qubits. So NSF-funded researchers are on the forefront of trying to understand what's the limitation of quantum computing and what's the potential. And you need engineers and physicists and computer scientists to work together to solve those problems. It's important to note that investing in quantum research is not something new to NSF. We've been investing in this area for many decades. We're simply taking a larger and deeper commitment in this important area of research. Our fiscal year 19 request is for $30 million new dollars in this area. However, many of our key country partners around the world are also making significant investments. The European Union announced a $1.2 billion over multiple years for quantum studies. Canada says $170 million for 3 university research centers. Japan has pledged $125 million, and China intends $100 million over multiple years. So you can see that NSF is a smaller part than the others, but we're collaborating with many of these other countries, as well as with our agency partners in the Department of Energy, Department of Defense, and the National Institute of Science and Technology. We hope to gain new insights into the behavior of matter at the smallest scale and develop quantum technologies that can transform measurement systems, information processing, communications, and computing. Achieving the next quantum revolution will require both investment in fundamental research and the development of a skilled workforce. So, harnessing the data revolution. I'm sure you've all heard it that data is the new oil, right? It's the key to new understandings about ourselves, our society, and the world that we live in. In many cases, this data has always been there. It's just been hard to measure or hard to store in large quantities. But given the huge advances in computing, networking, and storage, how can we harness this data to improve our world for the better? There's much basic research that's been done in the theoretical foundations of data science. However, every scientific discipline needs to have its own structure for the data that it uses: metadata, ontologies, APIs, etc. You can't just take a database with atmospheric observations and connect it with a weather model and ocean sampling data and try to understand how they fit together. You need to have those connections. There's a lot of potential, but you need some maps and glue. In the early days, I believe some of these connections will be more like chewing gum and baling wire. But as we get the fields matured and the definitions come, the values of those standard connections will be evident, and the standard practice will lead to bigger advances. I wanted to give you a few examples of the types of programs that we're launching in the Harnessing the Data Revolution. First, industrial and operations engineers have worked for years to optimize supply chains, to reduce cost and improve productivity. So the question that we're asking is, can we use what we know about supply networks to disrupt illicit ones? The projects that we're funding in this area so far are focusing on illicit drugs and human trafficking, taking the limited data that you can see into these networks, use it to infer the supply chain, and design optimal avenues to disrupt it. For example, supply chains for counterfeit goods take advantage of legitimate distribution networks, but are discoverable because of some transactional signatures that are different from those of legal transactions. One project will compare those analytics for both physical inventory and cyber activity to determine the patterns of illicit activity that distinguish them from those of lawful trade. Real-time learning and decision-making in engineering systems will also play a role in the modern engineering infrastructures, such as smart grid, transportation, water distribution, healthcare logistics, and advanced manufacturing. While complex engineering systems incorporate first principles physical models, they may not make full use of data that's available now in real time, high density, and high speed. So trying to bring that real-time data together with the physical models to make better decisions about how to operate the electrical grid or the transportation network is something that we're looking at in Harnessing the Data Revolution. So the last big idea is the future of work. So we've all seen it. The world of work is changing, and it's going to continue to change in the future. People are afraid that robots are going to take their jobs, and some jobs will be replaced by robots. But history tells us time and time again that although technology replaces some jobs, think of typesetting, weaving, agriculture, in the end, there are more jobs, although there are different jobs than there were before. And this disruption and the people that are affected must be considered. A recent article in Forbes studied the economic impact of industrial robots. With an 80% drop in the price of industrial robots and a huge growth in their use, productivity increased as expected, but so did overall employee wages. So the major transformation in work and the workplace is being driven by these new and emerging technologies: artificial intelligence, machine learning, Internet of Things, robotics. These new technologies are enabling instantaneous dynamic interactions between humans and machines in unprecedented ways. The transformation will change the way we produce goods, provide services, and collaborate with our colleagues. The social and behavioral sciences tell us that we need to change how we think about and study human-technology interactions in the context of work. Rather than characterizing technologies as a set of passive tools for humans to use in producing or efficiency in the workplace, we're conceptualizing these interactions as an evolving ecosystem in which humans and technology work symbiotically. One of the drivers of change in the world of work is the rapid pace of technological development. Computers are getting even faster and more powerful. The computing power that used to take up a whole room can now be found in your iPhone. The Internet of Things connects computers, machines, and sensors with each other so they can collect, share, and translate data into useful intelligence and action. Combining this big data with artificial intelligence makes everything smarter, but also allows technology to become autonomous and take independent action, such as a self-driving car decided to change its route based on traffic information. So why does this changing world of work matter to NSF? One reason is the concern that's being expressed is the effects on these emerging technologies on jobs, especially specific jobs. As you can see from these headlines and articles, one view is that automation is going to kill jobs, and there's a lot of fear associated with that. Another view is that job loss would be offset and even supported or surpassed by the creation of new jobs and new industries. For those of you who saw the wonderful movie Hidden Figures, you saw the women in the early 1960s at NASA who were the computers or human calculators lose their jobs doing calculations when the mainframe computer replaced them. However, they learned Fortran, how to program that computer, and this helped to launch the first job of computer programmers. These technology-driven changes in the world of work will impact all of the items listed here: employment, opportunity, labor productivity, economic growth, etc. So NSF plans to respond to this challenge through supporting fundamental science across all scientific disciplines, from computer science and artificial intelligence to social, behavioral, and economic sciences to engineering and new materials. We want to understand and build that human-technology partnership and design new technologies that can augment human performance and foster lifelong and pervasive learning with technology. So I'll highlight a few of the projects that we're funding. Is that in here? Sorry. In this area. So you might not be aware that about 20% of the labor force engages in shift work, which often leads to inadequate and poor sleep. So one of the projects that we're funding in the future of work is to develop an intelligent cognitive assistant to help people manage their circadian rhythms when they're going through shift work. It will measure their sleep patterns, stress levels, and infer their circadian rhythms and use that to make recommendations on when to sleep, when to eat, and things like that. They're going to test it originally on medical residents who are perhaps the most sleep deprived and circadian challenged things, and then they can look at how do these recommendations play out over time. Another thing that I'm sure you're aware of is that millions of people spend at least an hour each day commuting by car. Autonomous vehicles could allow part of that time that they're in the car to be used for work-related efforts. So one project is looking at how to combine autonomous driving technology with work that could be done in the car while keeping the driver enough engaged in the driving to be able to switch between their work tasks and their driving to increase efficiency. So we'll see how those go. I think there's some really interesting ideas on the future of work and how technology can enhance our work lives. I'm going to conclude my talk with Convergence, which is where I started. And this is a new idea that's coming out of NSF called Convergence Accelerators. So unlike small business accelerators that I'm sure you're all familiar with, these Convergence Accelerators have the goal of accelerating the convergent research that we're doing in the big ideas. I mentioned that all the big ideas are going to require convergent approaches to research, and that building this multidisciplinary team of experts can be time-consuming because you need to come together as a team and learn to speak each other's language. So we're envisioning, we hope, that these convergence accelerators will speed up that process of convergent research. So we believe that the convergence accelerators, by taking some ideas from commercial accelerators, will be able to, like I said, speed up the research. So they will have cohorts of teams working together on specific problems. And the teams will be able to learn from each other in a mentoring and networking situation. There'll be extensive educational and mentoring components, and have strong partnerships with academia, industry, and the government, including other government agencies. NSF will fund these, but we will look for partners from the mission-driven agencies. So although the convergence accelerators will be doing basic research, which is NSF's focus, the outcomes will be more intentional, trying to solve specific problems. So having multiple teams work on the same problem with multiple different approaches, and both sharing their findings with each other and competing with each other in what we call a co-opetition model, we expect the research to progress more quickly than if they were working in isolation. The strategic direction, or the problem to solve, will be set from the top, but the approaches to solve that problem will be diverse, coming from the bottom up. We hope to accelerate research where we can anticipate short-term deliverables using an approach that includes education and mentorships and rewards innovation, risk-taking, and transition to practice. So NSF will provide the organizational support for these accelerators, bringing teams together with their mentors and their networks. The inclusion of partners is important to broaden the potential for novel solutions. So this is a sketch of what we think the convergence accelerators might look like. I should say we haven't announced them yet, so this is, we've presented parts of this before, but the final format is still to be determined. But we believe that they will leverage the basic research that NSF has funded over the years. Our PIs and the partners will be coming into these convergence accelerators. They will form teams either organically by calling up their friends or through structured workshops that we will host with industry and government partners. We believe those teams need to be diverse, not only including multiple disciplines, but including multiple levels, some graduate students, some postdocs, some more senior faculty, to bring in those different perspectives to solve the challenging convergent research problem. Once the teams come together, we envision them working very intensely in a short, few months incubation process where a cohort of teams will work together, both cooperating and competing in a co-opetition. They'll have some on-site training where they'll learn about team building and communication skills and be able to teach each other from their expertise of their own individual disciplines, and can you continue to check in with the moderators during their team formation stage. At the end of the formation stage, the teams will have a pitch about what their idea is. And based on that pitch, as well as the coordinator's evaluation over the team formation stage, some of them will get a much larger grant to continue the research. Some of them may get a smaller grant to continue at a lower level, and others may be shut down. So we envision this will be a selection process, just like the proposal process we have at NSF, but much more accelerated. And we envision awarding prizes to the best teams at the end. So this idea is building on the model we have of I-Core, if you're familiar with that, with teams and cohorts. It also builds on the NSF INCLUDES program with the network collective impact approach. And we have, the standard NSF proposals and evaluation at every stage. So I'll leave you with a quote from the director of NSF and the brief recap of the 10 big ideas. So thank you very much for your attention, and I think I left plenty of time for questions.
My name is David Richardson. I'm a retired economist living out a pleasant life in Washington, D.C.
Can you tell if you're a member or not?
I'm sorry?
Are you a member of PSW or not?
One time I was. Does that count?
I think that means you're not.
Anyway,
You're
what
a
struck,
emeritus member.
what struck me when you're going through your big ideas is there are a couple of them that we know the solution for already. And you're talking about interdiction of drugs, for example. And what we should look at is back in the 80s when we destroyed the Medellin cartel, when we destroyed the Cali cartel. Now, you know that your drug program is successful when the price of drugs goes up. When we destroyed those cartels, the price dropped. And the reason was that we destroyed a monopoly. And all these other lower level people started competing with each other and the prices dropped. So part of the solution to this is to allow the monopoly to develop. Now, this will involve people killing each other, but they're professional criminals anyway.
We don't do speeches, okay?
All right.
You can have a discussion later. If you have a question, ask a question.
Okay, so anyway, it seems to me that we know at least part of that solution, and you might well direct your money in some other way.
Okay.
Thank you for telling us how to cure the drug problem. Next question, Bob?
Hi, I'm Bob Hershey. I'm a member. Could you tell us some more about NSF Includes?
More about NSF Includes. Well, so we started 2 years ago and we launched 70 of what we call these launch pilots. Now, October 1st of this year, so less than 3 months ago, we funded 5 alliances and a coordination hub. And the coordination hub is the backbone that's supposed to connect all these things together. Now, since they just started less than 3 months ago, I don't have any results to tell you, but we envision that they will be the one that connects all these launch pilots with Boeing and NASA and any other organizations that will join and have a standardized way to collect data, assess progress, and share best practices, as well as share things that didn't work. We tried this, it didn't work, right? So that they can improve the overall. So that's the idea of building the network with this coordination hub that brings everything together. So stay tuned.
There's a question in the back there with a gentleman with his hand up. Blue microphone.
Yes, I'm Joe Powers. I'm not a member. You said you had several facilities in the Antarctic. For the Big Idea in the Arctic, what kind of permanent facility would you have there? Or would that be something like a research base on Spitsbergen, or what exactly would that be?
So we have several facilities in the Arctic. We collaborate with several groups monitoring in Greenland, where we have some stations monitoring in Greenland. We funded what we call an LTER, long-term ecological research in Alaska, that's taking data over, long-term, these are funded for many years, but this was recently established within the last couple of years to take data across a large swath of Alaska. And then I mentioned the robots that are going to go under the ice and take measurements from below the ice of ocean temperatures and currents and things like that. So I think it's really not one answer, but trying to bring things together, as well as partner with other Arctic nations who are taking similar types of data and try to stitch that together across the Arctic. It's harder to have permanent positions in the Arctic because there's not as much land. Antarctica, of course, is a huge continent with a landmass, but there are, if you saw that map, right, there is land around the Arctic Circle where there are some permanent or semi-permanent monitoring stations.
Red microphone.
Yes, hi, I'm Jim Van Artsdale, and I'm a member. You opened your talk talking about how the NSF supports the national interest, which is certainly very, very important and a great example of why you don't want to be too laissez-faire in your economy. Certainly, China is becoming a much stronger competitor. Can you speak to what the Chinese counterparts of NSF do, how they act, and how and what NSF's strategy would be to maintain American dominance and scientific research and in the face of increasing competition from other nations?
So I'm not an expert on the Chinese funding portfolio, but I think they are somewhat similar. They have a Chinese version of the National Science Foundation that funds basic research at universities. They also have a large military that funds a lot of research and development, like we do through our Department of Defense. And I will say that NSF tries to partner with China as much as possible on the fundamental basic research, because we believe that fundamental basic research should be open for the whole world to use. If it starts to get too much into specific applications that would be defense related or have economic security implications, then partnerships get more tricky with intellectual property. But from NSF tries to fund basic research, and so we feel strongly that that should be open for collaboration. In terms of the amounts of funding, you read in the newspapers that China is pumping, large amounts of money into their universities and other types of research. And I don't have an answer of how we're going to counteract that. I don't think in the current funding situation we're going to be able to match them, but we still believe that we have a very innovative workforce, and through the NSF INCLUDES activities to try to bring in more diverse, outstanding, talented youth into STEM, we think that we have a potential to continue to compete. Maybe that doesn't answer your question completely, but.
Bob?
Bob Terry, a member. You mentioned the gravitational wave detector is one of the finest examples of what NSF has done over 40 years and tens of hundreds of billions of dollars. And
No, only 1 billion for
a
gravitational
mere
waves.
billion. See, right. All right. So,
But 40 years.
40
It's
years.
a long time.
The thing that strikes me is that was an organic growth with many workers, with incremental change and incremental discovery to find these things and move 7 orders of magnitude to the detector things that you need. The other ideas you've shown seem to be very top down. I'm curious about what are the metrics for success for those kinds of pictures, and what informs the new sort of top down way of structuring things with your changes and little incubators and stuff. What information or lessons do they take from something like the gravitational wave project?
So the 10 big ideas that we have are top down at a very wide level, but as you saw from some of the examples I gave, within, say, the future of work at the human technology frontier, there's a lot of different projects, and those are all bottom up. So we don't tell people which project to propose, we give them the broad scope. And so there's still a lot of diversity of approaches. Also, if you look at the 10 big ideas, we're allocating about 30 million for each. So that's 300 million out of an almost $8 billion budget. So most of our budget is not going to the big ideas. These are strategic, and it's a big chunk of our budget, but it's not the whole budget. Most of our budget is still going to the normal continuous things like LIGO and telescopes and basic research grants. So these are strategic to try to drive science in certain areas, but most of what we fund is still very much bottom up.
Green microphone, then the red microphone.
This is Charles Rong. I'm not a member. First of all, I would like to thank you for your excellent presentation about NSF contribution, the contributions NSF has made in the past, and also the impact that NSF is going to make in the future with the convergence approach to support the science and engineering effort. My question for you is regarding the navigating new Arctic. On the one hand, you mentioned that the ice is melting due to climate change. On the other hand, you also mentioned that to explore the Arctic is based on the estimate of the natural resources like fossil fuel, natural oil, natural gas, etc. So that I see that this is kind of conflicting, because we have climate change due to the relief of burning the fossil fuel, relieving the carbon dioxide. and then we are going to extract more of them from the earth. This is, I don't know, how would you explain this or clarify it to us?
So NSF is not extracting any oil. We are trying to understand the processes that are in place, and we want to make sure people understand the implications of those changes in the climate. We also want to make sure that the people who are living in those places will be able to react to the climate as it changes. And so I think we're more on the basic fundamental science and not on saying, I think if those oil reserves are opened up, someone will go get them. You know, I think it's in the current situation, unless we invent a renewable energy that makes it not economically attractive to extract oil from the Arctic. It's still hard to get it from I'll say challenging climates like even northern Alaska, but they are drilling up there. So that's I don't think we have NSF is not giving the answer to that question. We're trying to understand and put the science.
So you have a red microphone, then we'll take some online from the blue microphone, and then the green microphone over there. So 1,
Perfect.
2, 3.
Hi, my name is, sorry, too close. My name is Constantine. I'm not a member. Thank you very much for the presentation. I liked it that there was both the science as well as the way the science is being done and a lot of focus on that. And I had a question about the NSF INCLUDES program and what, if any, kind of focus it had on small businesses and entrepreneurs. I work with a lot of brilliant scientists and entrepreneurs who are building basically cultures, these new cultures from the ground up. And it seemed like most of the examples that you were talking about were within corporate environments that already exist. So I just wanted to find out, was there some kind of focus on supporting small businesses, entrepreneurs who are kind of trying to solve these issues by building a more inclusive structure and culture from the bottom up?
So absolutely, I didn't mention it in this presentation, but NSF runs a SBIR program for small businesses, and we also run an I-Corps program for training people how to be entrepreneurs. And both of those have strong focuses on broadening participation. In fact, a couple of months ago, we had an inclusion summit for the I-Corps teams to try to bring together people who were from I'll say underrepresented populations. I think they had a lot of HBCUs and some Hispanic serving institutions come together to think about how they could foster more entrepreneurship in their places. So that's maybe not exactly the same question that you have, but I think it is something that we put into the kickoff meetings at the SBIR workshops and things like that. So it is something that's pervasive across NSF.
Are there resources online that I could point my friends to on that?
Send me an email. I'm sure there are,
Okay.
but I don't know them off the top of my head.
Great. Thank you very much.
Online questions?
We have one question from an online viewer, Joel, who is a member of the society, who is watching from Maryland. He was disappointed that he didn't know about the idea machine ahead of the closure, and he was wondering if there's going to be another call for submissions to the idea machine and how it was advertised to the public.
So how is it advertised to the public? I think we sent out, I don't know how many thousands or millions of emails, but we had it on our website. All NSF PIs got informed of it, and I think they put ads in some like professional society magazines. I'm not exactly sure. So we expect this will take about a year, and so we will announce the next ones in summer of this year. And I think if it goes well, we might turn the crank again and see what comes up. But I can't guarantee that. But if it would come out in the summer next year.
So we have the green microphone now.
Hi, my name's Sabrina Mann, and I had a question and kind of a concept, if you could entertain it. My question was just about the NSF building off the blue line.
Green or yellow line. It's on the yellow line, but
Yellow line and
this
blue line?
week there's no yellow line, but
Blue
the
line.
blue line runs there. It's another.
If I were to go visit that, what opportunities or how could I apply myself there? Would I just kind of check it out?
So we have at the new building, we have government style airport level security. So you can't just walk in off the street.
Got it.
So you need to come visit someone
Okay.
But we do have a lot of opportunities. People come to the building all the time to be on review panels, to review proposals, to visit program officers, to attend workshops. So there's a lot of things going on. We have public meetings. Every directorate has an advisory committee, and they have public meetings, and you can say you want to come to that meeting, and then you can get a pass to come into the building. The National Science Board meets there several times a year. You can get a pass to come there. We have distinguished lectures that you can either watch online or you can get a pass to go to the building to watch the distinguished lecture. So there's a lot of opportunities to come visit, but you can't just walk in off the street.
Got it. Thank you. And then as far as my idea, I've just noticed working in my own field of cybersecurity that it seems like professionals in the cybersecurity field, when it comes to speaking with business professionals, there's a huge gap. And you were talking about convergence between sciences. Are you seeing any way in the future to create convergence between business and sciences so that communication and the time of error can be decreased between those two professions?
So I think one of the things that we do at NSF to try to, because I agree with you, there's a gap there too. This ICOR program we have that trains people to be entrepreneurs is taking scientists from the lab and trying to make them understand what it might mean to take a business. So we have some training for them in that program, but trying to scale it out more broadly, I think that's an opportunity that we could maybe consider.
Thank you.
Carl?
Carl Merrill, I'm a member. Early in my career, a lot of the work was supported by private foundations, not the government. And ones like the Rockefeller would pick a general area, and then they'd find people who were outstanding, and then they'd support them for the rest of their career. They'd meet with them every 4 years to see if they were productive. And that's where a lot of fundamental knowledge was gained. Does modern administration at something like NSF have any program like that?
Well, we have many PIs who have been consistently funded their entire careers by NSF. But you're right, they have to keep writing new proposals. It's not guaranteed. But if they're successful, they can write new proposals. And, if you're doing good stuff, writing the proposals is not that hard. And so we don't have a program like that, but we do have people who are funded continuously throughout their career, many of them, and they're very successful. The longest funding we usually have is 10 years for these centers, and they're not for single PIs, they're for teams.
Kristen, last question, I think.
Kristen Ferry, and I am a member, and I have to thank NSF for a fellowship for my PhD at Rice University. I notice that you have 3 electrical engineering degrees and you're a professor in the mechanical engineering department. I encountered when I had different degrees that I encountered academia in something of a state of consternation, not knowing what to do with that. So it occurs to me that I love your Convergence initiative. It occurs to me that you have your own story about interdisciplinary convergence as to how you got from an electrical engineering background to mechanical engineering department and so forth. Would you elaborate on that?
Oh, sure. It's not that, I wouldn't even say it's convergent. So my research is in robotics and control, which is kind of on the boundary. And when I was interviewing for faculty positions, I think I interviewed about half EE and half ME departments. Then the ME department that I joined was quite diverse at the time. I want to say there were 5 or 6 of us that didn't have any degrees in mechanical engineering. There were people from biology, material science, electrical engineering. One guy was from zoology, I think. I don't know, but it was chemistry, people studying combustion. So the department was very open to look at what can you contribute to mechanical engineering, doesn't matter what your background is. So I think that was the department I joined. And I think more departments are starting to be that way and not thinking so strictly in discipline, like I mentioned, the strict rules. So I think that's a trend that people are becoming more cross-disciplinary or interdisciplinary. When I teach the graduate courses in control, they used to have 3 numbers: electrical, mechanical, and aerospace. And now they have civil engineering because they've issued a program in structural control. So now I stand up in the room with a bunch of students, and they're all taking different classes, but it's the same class. Let me just have different numbers, right? Depending on which one they registered for. So I think that's, in control systems, we tend to go pretty smoothly between departments.
Now, I think that was the last question. So before you go, I'd like to give you a small gift, a framed copy of the announcement of your lecture and a copy of volume 1 of the PSW bulletin, published in 1874.
Great.
So thank you very much.
Well, thank you very much. I enjoyed it.
Before we go, a few closing announcements. As you know, PSW depends on members and sponsors. And if you're not a member, we'll ask you to please join. If you are a member, please consider giving more, becoming a sponsor, or becoming active in the society. If you have any questions about membership, becoming a member, or doing more, please see our membership director standing over there with his arms crossed, Lloyd Mitchell, and also our corresponding secretary, Robin Taylor, who's sitting at the computer, or our social media director, Anne McQueen, who's sitting up here by the soundboard. If you're not a member and you want to join, it's easy to do. There is a join button at the upper right-hand corner on the homepage. Push that button. It'll bring up a screen. It explains a little bit about membership. It has a membership button. And when you press that, you'll get to a membership application. And when you fill it out, get to the bottom, there's a pay your dues now button. If you pay your dues now, we won't let you be a member and we won't return your fee. No, just kidding. You'll almost certainly become a member. And if for some reason that doesn't seem apt, your fee will be returned. Membership is open to all who have an interest in science. So for those of you who are members, if you haven't paid your dues yet, you should do so immediately, because the election is coming up and only dues paid up members are allowed to vote for the open seats on the General Committee. Please keep in mind, PSW is a nonprofit educational organization, tax exempt under Section 501c3 of the Internal Revenue Code. Contributions are tax deductible to the extent permitted by your friendly IRS. And all members in good standing can wear the PSW rosette, which you can't see, this nice little blue rosette. And if you wish to purchase one, they're $15, and you may do so at the rosette table in the back of the room there. Savannah is showing you the table, a la The Price is Right. The next lecture will take place at 8 p.m. here in the Powell Auditorium on January 11th, 2019. This will be the annual President's Lecture, and the speaker will be Lee Cronin. Regius Professor of Chemistry at the University of Glasgow in Scotland, United Kingdom, for now. He will be speaking on the digitization of chemistry, personalized drugs on demand, some of which was featured in recent pieces in Science and highlighted in the November 29th issue of Chemical and Engineering News. The rest of the spring schedule is complete, except for a few details, and the speakers and the topics have been posted to the PET website. Details will be added as we go forward. January 25th, we have Todd Coleman of UCSD who will be speaking about wearable sensors. On February 8th, Raman Sundran of the University of Maryland will be talking about supersymmetry and multidimensional spacetimes. February 22, we have Davey Bach of HHMI Genelia, and he'll be talking about mapping brain connections, neural mapping. On March 8th, we have Ramesh Gopinath of IBM, who will be talking about blockchain's use in commerce. On March 22, we have Jim Garvin and friends, who have not yet been named, who are going to tell us about Venus and why we should be going back to Venus. On April 12th, we have Mary Angela Lasante of Princeton, who will be talking about dark matter. On April 26th, Kim Jamda from the Scripps Research Institute will be talking about his work to develop vaccines that create immunity to drugs of abuse. And on April 29th, I'm very happy to announce that we have a very special event. The 29th is a Monday. How many of you think Pluto is a planet? How how many of you are devastated that Pluto has been reduced to dwarf planet status? Well, this is a topic of great heat and interest in the planetary sciences community. And on April 29th, on Monday, we're going to have Alan Stern, who is the PI for New Horizons, who, as you might imagine, is a proponent of Pluto's planetness, and the former president of the International Astronomical Union, Ron Eckers, who is a proponent of the opposite point of view, to present a history of yes, it's going to be about 15 minutes of a history of planets and why, what makes a planet, what has been the common understanding of planets, and how we came to know about the planets that we know about, maybe a little bit about the planet that we may not know about, that either is there or isn't there. And then they'll argue for their points of view on why Pluto should or shouldn't be a planet. Now, lest you think this is just a debate in which people have opposing opinions and nothing to support them, you couldn't be more wrong. There's actual physical reasoning behind these points of view. And so our very own Kirby Runyon and Alan Stern have written a piece in the scientific literature proposing a definition for what's a planet based on, does it circumnavigate a star? What is its mass? Does it form a sphere? And criteria like that. And so we're going to have a lot of fun with this. And I think you should all come, and I think you'll enjoy it greatly. And we will be rounding up at this point. It looks like the last lecture will be May 17th. It will be the 87th Joseph Henry Lecture, given annually by PSW. And the speaker will be Brian Keating. And some of you know Brian Keating from his very popular book, although unpopular in some quarters, on why the Nobel Prize is a nasty beast. But it has a lot of very interesting stories about the Nobel Prize and who should have won it but didn't, and the effect that it had on him in trying to seek results that would win him the Nobel Prize. I'm hoping you won't talk about that. I'm hoping you'll actually talk about a science that he does, which is to look at the cosmic background radiation and other physical, what do I want to say, signals, to understand what happened and inflation at the very beginnings of the universe as we know it. But we'll see what he wants to talk about. And that will be rounding up our lectures. So my final word is that the social hour ends at 10:30, after which PSW members and some guests meet across the street at the Fairfax Hotel Lounge. If you want to join us there, please speak with Corresponding Secretary Robin Taylor, or Membership Director Lloyd Mitchell, or me sometime during the social hour. Please use the side entrances to exit the building. And I will now accept a motion for adjournment of the 2400th meeting of the Society to the Social Hour. I know, you always do that. You don't even have to raise your hand. I thought I could get participation by some other member. Any other member? Okay, we got one member there. We have a second. You can second. Bob seconds. All those in favor? Aye. All opposed? All right, the meeting's adjourned to the social hour.